Hello, Math 1224. This is Dr. P with Lesson Launch 701, the bear trap. So what you're seeing here in this image is the graph of the function f of x equals, let's see, put this over here, f of x equals 1 over the square root of x cubed plus 4. And in this video I want to ask the question, can we evaluate the integral from 0 to infinity of dx over square root of x cubed plus 4? And if we can't evaluate it, can we say anything useful at all about it? For example, this is an improper integral. Do we know whether it's convergent or divergent? That would be interesting to know. So first of all, I want to see if we can evaluate this integral using the techniques we talked about in the last section. That is, by just integrating dx over the square root of x cubed plus 4, and then taking the limit of a definite integral, of a proper integral from 0 to b as b goes to infinity. So I'm going to see if we can evaluate this integral that way. All right? So to do this, we might start by asking ourselves, okay, what is the antiderivative of 1 over the square root of x cubed plus 4? What is that anyway? Now, I look at the integral table and I don't see anything like this. I don't see anything that has square root of x cubed plus a constant in there. And I don't see any substitution that's readily going to work because I've got an x cubed in the denominator. If I had a 3x squared or any constant times x squared up here, I might be in business for substitution, but I don't have that either. I don't see any straightforward way to integrate this by parts. I don't know what I'd choose the parts to be exactly. I don't know how to integrate 1 over the square root of this. If I did, I'd be done. And if I differentiate this 1 over that square root, I'm just going to make things worse. But one thing I could try is I could look at this expression here, see an x cubed plus 4 and think, oh, maybe a trig substitution will work. So what if I try to make x cubed equal to, let's see, what would I want that to be? I think I'd like for that to be 4 tangent squared theta, because then 4 tangent squared theta plus that 4 there would equal 4 secant squared theta, and at least I could get rid of the square root. That'd be kind of nice. So let's see, what substitution would be needed here? I'd need x equal to the cube root of 4 tangent squared theta, all that to the 1/3, and then I need dx to equal, let's see here, 1/3 times 4 tangent squared theta to the minus 2/3, and then don't forget we need to use the chain rule on that, so I'm going to need times, and then what's the derivative of 4 tangent squared theta? That would be, I guess that would be 8 tangent theta times secant squared theta d theta. Okay, so I could go ahead and just substitute all of that into this integral here, this one right here. That would get rid of that square root, but then, I mean, look at what I have to contend with in the numerator now. Oh, this is brutal. I don't think I want any part of that. Just looking at that kind of makes me sick. That's calculus barf there. Okay, anyway, so let's not do that. Let's do something else entirely. I'm just going to get rid of all this. This was foolish. And by the way, my not being able to do this, it doesn't mean that we couldn't evaluate the integral, but I don't know. I've been around a few of these, and I've not had a very good experience with them. So I think integrating this directly, evaluating the integral, is going to be a tough thing to do. So I'm just going to get rid of all that, and I'm going to go back to my graph here. Maybe I can't evaluate this integral exactly. That might be difficult to do. In fact, it may be impossible to do. I might never find an exact value for this. But one thing I can try to do is determine whether this integral converges or diverges. And actually, we have quite a bit of latitude when we look at these improper integrals. If we have the right skills in place, we can figure out in many, many cases whether the integrals will be finite or infinite. So what I'm going to do is I'm going to think about the behavior of this function. Think about long-term behavior, which is something that you have some practice with from Calculus 1. When you did limits at infinity, it was all about thinking about the long-term behavior of a function. So I'm going to think about the long-term behavior of 1 over the square root of x cubed plus 4. What does that behave like? So try and think of some simpler function than that mimics the long-term behavior of f of x as x approaches infinity. We don't care so much about whether it's like this, whether it's similar to this near 0, or anywhere in here. We just care about our function mimicking this as x goes to infinity. All right, so I don't know about you, but my instinct here my spidey sense says that 1 over the square root of x cubed plus 4 is kind of like 1 over the square root of x cubed as x goes to infinity. Those behave kind of like one another because as x goes to infinity, this is getting really huge. 4 is just going to remain 4. This is going to be very small compared to what this is as x goes to infinity, which means as x goes to infinity, this plus 4 is going to become more or less negligible, and this function here will behave much like this one. Now the question is, can I say anything useful about what this function does, what the integral of this would look like as x goes to infinity? Well, first of all, if I try to evaluate the integral from 0 to infinity of dx over the square root of x cubed, I'm going to get into some trouble that I actually don't want to get into, because at x equals 0, this function has a discontinuity, which this one doesn't have. When x is 0, this is perfectly fine and reasonable, as you can probably tell from the graph. But this function here, at 0, this function is going to have a vertical asymptote. So instead of looking at the integral from 0 to infinity, I'm going to change this to the integral from 1 to infinity and try and evaluate that. And I'm going to change this to x to the 3/2. That's the same thing as the square root of x cubed. It's just written differently, and a lot easier for me to think about how to integrate it using the power rule. So this integral is a limit as b goes to infinity of integral from 1 to b of x to the minus 3/2 dx. And then that's going to be the limit as b goes to infinity of, let's see, what is that? That's 1 over negative 1/2 x to the minus 1/2 from 1 to b. So that's the limit as b goes to infinity of, let's see, at b that's going to be negative 2 over square root of b, I think. You might want to check my algebra here, plus 2 over the square root of 1, which comes out to the limit as b goes to infinity of 2 minus 2 over root b. Well, what does that do as b goes to infinity? That last term there is going to go to 0. So that part's going to go to 0, and this whole limit here is going to be 2. So this integral here is very finite. It is convergent. So this one is convergent. That's to say nothing about this one. We don't know exactly what the integral from 0 to infinity is going to do. But I'm going to focus on this one. And now I'm going to come back up here. Let me just zoom out a bit there. Okay. So what we've done is we've shown that this integral from 1 to infinity of dx over x to the 3/2, that converges, that has a finite area. So look at this graph, look at this function, and compare with this function. Remember, that came from looking at this. Well, one thing that we know, let's see, I'm going to pick a new color here. There we go. Beautiful. One thing that we know is that 1 over the square root of x cubed plus 4 is always less than 1 over the square root of x cubed for x greater than 0. The reason for that is that this fraction here has a larger denominator, so we're dividing 1 by something bigger over here, which means we're going to get a smaller result than if we divide by square root of x cubed. So what that means is that this function, 1 over the square root of x cubed, now it is going to have an asymptote at 0 because it's that denominator is 0 there. But, and I'm really just eyeballing this here. Actually, let me do that again, because I know that at x equals 1, the value of this function is going to be 1. But in the long term, the graph should look something like this. Now, I'm really sketching here. But that's what you're going to have to do a lot of the time, is just get a sense of overall behavior and not worry too much about details. But one thing that we know is that this curve always has to be below this curve, because this function is always less than this function. And, well, what did we do here? We showed that this area here, from 1 to infinity, is finite. In fact, it is equal to 2. So I can also say something about this area. That area there, from 1 to infinity, must be less than or equal to 2. In fact, I could say it has to be less than 2. And then this area here, let me just color that in. Okay, that area is the area that's not yet accounted for. Remember, we were trying to go from 0 to infinity. But this area here, that has to be finite. In fact, I could say a little bit more about it. I know that the greatest height it's ever going to have is going to be 1/2, and the width of this area is 1. So I think that area is going to be less than or equal to 1/2. In fact, I'm pretty sure about that. So anyway, in summary, I can't say a whole lot about the exact value of this integral here, this one right here. But one thing I do know, after doing all of that work, is that, actually I'm just going to see if I can get rid of this. There we go. I can say that this integral is finite, that is, it's convergent, and its value is less than or equal to 1/2 plus 2, which is 5/2. Okay, I'm not saying that the value is equal to 5/2. I'm saying the value is less than or equal to something that is 5/2. And so there you go. Sometimes you get an integral you don't know how to evaluate exactly, but it's improper, and you can still figure out whether it's convergent or divergent. And in fact, if it's convergent, you can even put an upper bound on it. So anyway, we're going to systematize this thinking a little bit more in the next video. The idea here was just to give you a sense of what the problem is and what are some of the techniques that we'll use to solve this type of problem. So stay tuned for the next video.